We're rolling, finally.
Okay, I'm recording. So we would say then that we could identify that this place right here is an absolute max. And then this place right here would have been our absolute min, right? Easy to do. You'll get some practice problems to work on. I'm going to be gone, like half the period tomorrow. So I want to get through some stuff, and then you guys get to just work really probably all day tomorrow. I'll be able to answer questions at the start, and then you can work on the other stuff. So that's a pretty good summary of the stuff that we did last week. All right, so now we want to look at a couple new things. We want to look at how we can use. We're working towards what's called the first derivative test. So our goal for today is we want to find ways to very efficiently locate relative extrema. Okay, and we know they have to occur at critical numbers, but how are we going to organize our search for these things, right? Well, let's remind ourselves about a couple facts, things that we sort of alluded to last week, but we never really said it. So a function is increasing when relative to the first derivative. On what intervals would a function be increasing? What's it mean for a function to be increasing? Without being, no fancy words here, what's it just mean? Positive slope. Yeah, it's going uphill from left to right. Okay. So how does that relate to the derivative then? Okay, positive derivative. So an increasing interval would be an interval on which the derivative is positive, right? Decreasing interval, conversely, would be an interval on which the derivative is negative. Okay? It's an easy way to look for it. Okay. So then, if we wanted to make a table, and let's look at an example of a function here. Okay, let's look at a function like this, f of x. We're going to analyze this. We want to find the intervals on which the function is increasing and decreasing, and then find all of the relative extrema. Okay, and we're going to utilize one of those tables that we started talking about last week. Well, in order to find critical numbers, or to know where it's increasing or decreasing, what do I have to do with this function?
Take the derivative.
Yeah, there's where the calculus comes in, right? We got to take a derivative. All right, so here's our function. What about our derivative? What can we do to get a derivative here? We've done this a lot, but we could use the quotient rule. That'd be fine. What else could we do? Okay, so we could, because I've got a monomial factor in the denominator, right? We could just separate this into different terms. I could just divide each term on the top by x squared separately and get two simple power rule derivatives. So one thing I could do here, and they both would work, but this is easier, isn't it? X to the fourth over x squared is
X
squared.
X to the square, yes.
And then 4 over x squared is just 4x to the minus 2, right? Okay. So then if we were to differentiate this thing, what are we going to get?
2x.
Minus 8x to the negative 3. Okay. And if we wanted to write that maybe as a rational function then, I could either write this one as a fraction and get a common denominator, or you might remember something that we did is we always try to factor out the greatest common factor, the least common powers. So I could take a 2 out, agreed?
Yeah.
What's the least common power of x?
-3.
Negative 3. So I could factor out a 2x to the negative 3, leaving me with what? What's 2x divided by 2x to the minus 3? So this is 2x divided by 2x to the minus 3. The 2's cancel. X divided by x to the minus 3. When I divide like bases, I subtract, right? So x to the 1 minus negative 3 would be x to the 4th. Right?
Yeah.
Okay. Everybody see that? Okay. And then what about the second part? Second part here, we'd be dividing 8 x to the negative 3 by 2 x to the negative 3. So the x's would cancel, and I would just get, it's a minus, isn't it? So I would just get minus 4, good?
Yeah.
Okay. And so then our first derivative, we could get, if I write it as, if I write it as a rational function, I'm just going to get 2 times x to the 4th minus 4 over x cubed. Okay, but we could have just done quotient rule once again. Or the other thing we could have done is right here, and you take your pick. I mean, I don't think it matters that much. I don't want to spend too much time on this, but this is good review. We haven't done problems like this in a little while. Take your pick. You see, we also could have done this. Instead of factoring out the greatest common factor of each of these, I could have also just written this as 2x minus 8 over x cubed, and then just got a common denominator, right? Multiplied this one through by x cubed over x cubed, right? And that would have given me 2x cubed minus 8 over, or 2x to the 4th, sorry. Over x cubed. If I factor a 2 out, there's my 2 times the quantity, x to the 4th minus 4 over x cubed. I mean, you take your pick, right? Yeah, there's any number of ways we could come up with that. But once we're there, okay, now what? Okay, now we've got our first derivative. So let's try to find intervals where the function is increasing and decreasing, and at the same time maybe find all the relative extreme. So how am I going to go about my search for where the function is increasing and decreasing? If you think about that, I've got to find all the places where the derivative is positive and all the places where the derivative is negative. Okay, what are the only possible boundaries between those regions? Okay, well, one possibility is that the derivative could be 0 in between, positive and negative, right? There is one other possibility.
Undefined.
Could be undefined too, right? There could be like a break in the derivative, or see what I'm saying? There could be some other weird things going on where, I'll give you an example. Like what if we had something like this, right? So here's our function. It could go from increasing to decreasing where the function has a 0 derivative, but it could also be some place where it's got a sharp corner, right? So we got 2 possible places where that could happen. So if you think about our search then for the boundaries between increasing and decreasing intervals, well, what are those places where the derivative equals 0 or it's undefined? What do we call those numbers? Yeah, those values of x would be our critical numbers, right? You get the idea? So really, we're killing 2 birds with 1 stone here, aren't we? We're by finding the critical numbers, we're finding all the possible boundaries between regions of increasing and decreasing behavior for the function, right? So this all boils down to an organized search for critical numbers, okay? So there's 2 different kinds. There are going to be places where the derivative is equal to 0 or where it's undefined. So let's look at both of those possibilities, right? So now we're searching for critical numbers. Okay, so type 1 would be where f prime equals 0. Okay. Now, why do you think we spent time putting this function into a rational form like this, where it's something divided by something? If I hadn't done that, if I had just left it like this, That would not have been as convenient, right? How come? If I had just left it like that, which is this, before we have the yellow stuff in there, right? 2x minus 8x, 8 over x cubed. Why is that maybe not quite as good? It would have worked, but you have to do a little bit of extra algebra to find out where that's equal to 0, don't you? Where, you know, for what values of x is that expression equal to 0? If I write it as a rational function, where is a fraction always equal to 0? When the numerator equals 0, right? See my point? So if we write this in a rational form like this, if we're looking for where the derivative is equal to 0, well, that's just a numerator question. All we've got to do is ask, well, where does the numerator equal 0, right? So where does the numerator equal 0? The numerator equals 0, wouldn't you agree, when that expression, we don't care about the 2, when x to the 4th minus 4 equals 0. Agreed? So f prime equals 0 when x to the 4th minus 4 equals 0, right? So all we have to do is just solve that little mini equation. Agreed? And they didn't give us any, for this function, they didn't impose any domain. So the domain of the function is just going to be the natural domain of the function, right? Every place where the function exists. Okay, now do you see that it might have been a good idea for us from the very beginning to ask that question? Where does this function exist? Okay, we kind of glossed over that step, but in hindsight, that would have been a good one. So where is this function? Where does it exist? Right? Where does that function exist? Probably easier to ask is where does it not exist? It doesn't exist at 0. How come? Because you can't divide by 0, right? So there's only two kinds of places you're looking for where you're trying to find the domain of a function. There's only two red flags that pop up. Anytime you have an even root, like a square root, well, you know, if we're looking for real results, which we are, you can't take an even root of a negative number. So we'd have to, that might restrict our domain, right? If you have a square root or a fourth root or some even root in there. And then the other one is if I've got variables on the bottom of a fraction somewhere, right? If I have variables on the bottom, we know that the bottom cannot equal 0. And so really, here's what the algebra could look like for this. X squared cannot equal 0. So if I square root both sides, what do I get for my domain? If x squared cannot equal 0, then what does that amount to? What is x never equal to? 0. Yeah, if I solve for x, my domain, and I really should probably just put that up there, is, well, I'll put it down here for now. X is not equal to 0. So 0 is the value that's excluded from our domain, but our function exists everywhere else. Okay, that's pretty good because that eliminates, could we have a critical number at 0 then, I guess is my question to you? No, critical numbers only make sense where the function exists, right? You obviously can't have a derivative where the function itself doesn't exist. So you can limit your search for critical numbers to numbers that exist in the domain of the function. So in hindsight, that's a step we always want to do before we even do any calculus, is we want to know what is the domain of the function. Got to write that out. Oftentimes it might be all reals. It's not this time though. Okay, so then where are our critical numbers? We're just going to solve this little equation. Well, how do you propose solving this equation? This is good review.
Or add 4 to both sides.
Okay, we could. There's a couple ways we could do this one.
Or you could factor it.
Okay, or we could factor it. Now let's look at both methods here. We're trying to ask, when is f prime equal to 0? And isn't it funny in math, when you get to this level, you have all these discussions like there's plan A or plan B. And a lot of times I'd like to take you through both of those so you can see the relative merits and you kind of get an idea where, okay, what's the best way to do this in the future? Which one will I choose? If I just isolate the x to the 4th, I get x to the 4th, so this is plan A. I get x to the 4th equals 4. Now what?
You take the 4th root.
Okay, now it's dangerous to take the 4th root here because when you start taking roots that are higher than a second root or a cubed root, you begin to ask questions like, okay, does that mean I include a plus or minus or not? Right? There could be, you could miss some zeros that way when you do that. So ideally, what you want to do is you want, if you're going to isolate a variable by taking roots, it's safer to take only successive square and cube roots, right? So if I were to square root both sides, what would I get? I'd get x squared equals plus or minus 2, right? Okay, and then now if I'm looking, and when we're looking for real roots, it's not going to matter, right? But what if we were looking for all complex roots, which someday you will be doing, right? At some point in math, you're going to be looking for, you're going to be doing calculus of complex numbers, right? So complex analysis. And then the danger of if I took a fourth root of both sides, all I would have gotten was plus or minus square root of 2, right? But now if I split this up, look what happens. I get x squared equals 2 or x squared equals negative 2. And now I'm going to get x equals plus or minus radical 2, or I get plus or minus square root of 2 times I, right? Get the idea? So if you're going to isolate a variable, right? You want to make sure that you're always just taking successive square roots, which leads me to believe that a better way to do this is plan B, which is factoring, okay? I think it's always safer to do, especially if you're looking for all complex results. If I factor this is just a difference of squares, isn't it? Right? So I could factor that into x squared minus 2 times x squared plus 2 and apply the zero product property. Right, you get the idea? Okay, we'll jump right back into this because this is kind of an important thing. Jenna, you get what I'm saying on that?
Yeah.
Yeah, okay.